Hello everyone. Thank you for attending our presentation. Today I'll be discussing wind resource assessment. In this project, we discuss our hybrid solution for predicting offshore wind from limited onshore measurements. This work was done in collaboration with Dr. Alfredo Penna and Dr. Jake Badger from the Technical University of Denmark, DTU, and received funds under the H2020, the Future and Emerging Technologies Program Agreement. The outline of this presentation goes as follows. One, an introduction about wind resource assessment. Two, the algorithms used for the data fusion. And three, a description of the test case. Four, the pre-processing of data. And finally, five, our data fusion algorithm for predicting offshore wind from limited onshore data. So why do we need wind resource assessment? The answer is that using wind resource assessment, we're able to understand the potential of any location and of how it can become a wind farm and how much electricity we will be able to generate throughout the year. Here we see the four most common approaches for the measurements. We start from masts. These are very accurate methods that can be used for national local regions. Unfortunately, they cost around $15 million. The second method is floating lidars. Lidars are a great source of wind speed measurements. They are accurate and not as expensive as masts. However, they are extremely unreliable and provide low availability at offshore locations. They also often get damaged because of the harsh weather conditions offshore. The third method is using SAR images, another accurate technique that requires satellites for operation. And finally, the fourth method is using mesoscale simulations. These provide continuous data across all points of the location and at all times of the study, but they are of a very low fidelity and low accuracy. Our data fusion algorithm works on combining two different methods, a temporal fusion and a spatial fusion. We here see that we have two measurement points, one onshore and one offshore. The onshore point has a continuous time series of a low fidelity generated using the WRF simulation and a sparse but accurate time series generated using the LiDAR equipment. We merge both techniques using multi-fidelity Gaussian process regression and end up with a complete continuous time series which is more accurate than the original WRF and is complete and continuous unlike the LiDAR data. We then carry the tests to the offshore point using our spatial fusion technique, NARCS, the nonlinear autoregression with external input. We train the neural network with the result of the temporal fusion and the WRF simulation data of the offshore point, and we test it on the LiDAR of the onshore point. And as a result, we get a time series which is more accurate than the WRF simulation and is continuous, again, unlike the LiDAR measurements. In the figure below, we show the availability of the techniques, the LiDAR measurements compared with that of the WRF simulation. The red dots represent the sparse high fidelity measurements and the blue rectangle represents the WRF data. So the LiDAR data is sparse in both space and time, whilst the WRF data is available at every point and every time step of the process. For the algorithm of the temporal fusion, we use multi-fidelity Gaussian process. Our technique uses two different layers, which considers the high fidelity data FH as a function of the time and the low fidelity data FL. And then we perform Gaussian process, which consists of a mean function M and a covariance matrix K. They follow the Bayesian approach, which measures the uncertainty between the observed and the predicted data. In a further attempt, we take the derivatives and other additional data into account, and the high fidelity data is then a function of time, low fidelity data and its derivatives. And in this experiment, we're going to show introducing new additional information. Our second algorithm defines the spatial fusion, which includes a neural network that predicts points in a series YT from past points and additional input xt to predict yt plus 1, a point which is a step ahead in time. Here, yt represents the high fidelity data, while xt is the low fidelity data. We see the nonlinear function for predictions along with the framework for the NARCS model, showing the training data and the multi-layer network. We now move to our case location at the west coast of Denmark. The wind condition was collected at the Rune project using LiDAR measurements and WRF simulation. As previously mentioned, the WRF data is available at every point, while the LiDAR is generated using two LiDARs in LiDARs 1 and 3, which perform dual Doppler scans, measuring a line of sight of 36 points at a height of 50 meters above sea level. For data processing, we used EWT, or the empirical wavelet transform, to smooth the data and reduce the fluctuations in the time series. This helps making it more suitable for Gaussian process. In the figure, we see the original data in blue with very spontaneous and sharp fluctuations, and the process time series, our output, using empirical wavelet transform in black, which is now ready for Gaussian process. Now we show the results of our temporal fusion, the temporal section. The tests were conducted on 3 different hybrid techniques. The first contained only the WRF simulation data and the LiDAR measurements. Hybrid 2 using the WRF, LiDAR, and derivatives of the WRF time series. And finally, hybrid 3, which pre-processed the WRF data with empirical wavelet transform and using WRF and its derivatives along with LiDAR measurements and the vector components of the wind speed. On a separate iteration, we also measured the RMSC of predictions at all 36 points using all 3 hybrid methods and compared them to the WRF simulation. The results show that all hybrid techniques are more accurate than the WRF, with hybrid 3 outperforming all other methods significantly. We also tried using 3 different sources of data, a LiDAR which has the highest fidelity, a high resolution WRF, a medium fidelity, and a low resolution WRF with low fidelity. The results suggest that it could be efficient as it was able to outperform our 3 hybrid techniques, which is the orange line. Now we move to our spatial results. We linked 2 points together with a neural network, an offshore and an onshore point. We trained the network with WRF at both points and then tested it on the LiDAR measurements of the onshore point. We generated the red dots in the right figure. In that figure, we show the WRF and LiDAR of the offshore point for reference. They weren't used in the training of the data. Only the LiDAR wasn't used in the training of the data. For reference, and how NARCS was able to produce results, and they actually showed very close results to the LiDAR measurements. We then show the aim or the goal of our main project, which is using both techniques together, temporally and spatially. The intermittent measurements at the most onshore point is used to estimate the wind at the most offshore point. So our final result is, as I previously said, we merge the result of the temporal as input for our spatial fusion. We were able to generate a continuous line, which is the black line here, which represents the LiDAR measurements across the entire experiment duration, more accurate than the WRF simulation, and continuous and extended, unlike or different from the LiDAR measurements. The RMSC was less than 9%, which is it outperforms the state-of-the-art multi-fidelity Gaussian process. So the summary of our work was the intermittent LiDAR measurements is completed and extended. We only had 133 LiDAR measurements in 3 months. Now we have 10,000 measured data throughout the entire experiment. The onshore measurement can be used to estimate offshore wind with an RMSC around 9%. For our future work, or the work that we're currently working on, we're extending our multiple fidelity layers. This is using extra layers of sources, so different sources to generate the data, which is different resolutions for a WRF simulation, or using WRF with LiDARs and data generated from masts, so just different sources. We're also taking our experiments from one dimension, which is a single point with varying with time, to multiple points in a plane, showing different points at the same sea level, height above the sea level. And then we're going to be testing the algorithms on different sites as well. We worked with the DTU on their experiment that was published in 2018. We're going to test our algorithm on cases or like sites in Brazil. And like here is our contact details. You can speak to me directly or Dr. Atanas and Dr. Donald, my main supervisors. This presentation is recorded and will be uploaded to the HPCWE project.eu website. It's attached here. And thank you. I'll now take your questions.